Hello everyone, my name is Ali Duri from Queensland University of Technology, and today I'm going to present our paper titled 3-Chain, a fast and lightweight consensus algorithm for IoT applications. In recent years, blockchain has received tremendous attention from both academia and practitioners because of its salient features. These features include the distributed management of the blockchain. So in blockchain, all the communications between the participating nodes, which is also known as transactions, are broadcast and verified by all the participating nodes in the network. So this ensures a sort of a distributed management of the ledger without relying on a central controller or a trusted third party. So in blockchain, particular nodes in the network collect the transactions and then verify them and append them into the blockchain by following a consensus algorithm, which ensures that all the nodes in the network have the same view of the blockchain. And also it prevents the malicious node from flooding the network with fake transactions. And in this way, it introduces sort of a distributed trust between the participating nodes. In blockchain, all the transactions are visible by all to all the participants, and it is accessible because it's been stored permanently in the ledger, which introduces a high transparency and auditability. And also, each blockchain user is known by a changeable public key, which introduces a level of anonymity for the users. Uh, as can be seen here in the blockchain, the blocks contain the hash of the block content and the hash of the previous block header. So this means that if I'm going to change a transaction in this block, then the corresponding hash will change, and then it wouldn't match with the hash that has been previously been stored in the block 2. So this way, this ensures that the blockchain achieves high immutability, and sort of it's not possible to remove or modify contents of the blockchain. Because of these features, blockchain has received to be as its attention to be applied in Internet of Things as a secure and distributed um, architecture. But there are challenges to apply blockchain in sort of a larger scale networks like IoT. So the first challenge is that the existing blockchains, or better to say the consensus algorithms, demand high computational resources, which is to technically is to make sure that uh, the, the the ledger cannot be controlled by the malicious nodes, and so it requires a sort of a computational overhead. And all the transactions and blocks needs to be broadcast and verified by all the participants. Where in an IoT setting with millions of users, it wouldn't scale because of the million of transactions that will be generated in the network. Uh, in blockchain, the throughput has been defined as the number of transactions that can be stored in the ledger per second, while the existing blockchains or the consensus algorithms have very low, limited or low throughput. While in IoT, there are millions of transactions that needs to be generated and needs to be stored in the blockchain per second. And also, the existing consensus algorithm incurs a significant delay before storing the transactions, while IoT demands a sort of real-time applications. So most of these challenges are tied back to the consensus algorithm. So the consensus algorithm basically makes sure that the first thing is that the validator is being selected in a randomized and unpredictable manner, and sort of it would be easy for the other nodes to verify that actually the validator has been selected randomly. And it also makes sure that all the nodes in this network have the same view of the ledger, which I will come back to this later. So so for now, we're focusing on the validator selection, or the nodes that is going to store the new blocks into the blockchain. So in this paper, we propose a 3-chain, which bases the validator selection on an existing function in all blockchains, which is the hash function output. So 3-chain is a leader selection algorithm. So it selects a leader, and then that leader would be responsible for storing blocks into the blockchain for a particular period of time. So as I said, it relies on the hash function. So we all know that the hash functions receives any sort of size input and generates a fixed size output, which is randomized. It is unpredictable and it would be easy to verify. So it ticks all the boxes for a consensus algorithm. So tree chain introduces randomization in two levels. The first is the blockchain level and then the transaction level. So let's start with the blockchain level and let's explain it through an example. So assume that we have this network shown here, and this gray nodes are the nodes that are interested to be a validator nodes. Initially and during the bootstrapping, so all these nodes will generate a transaction saying that, hey, I'm for instance node 3 and this is my public key and I'm interested to be a validator in this network. So what happens next is that all these nodes will broadcast this to the whole network, and they eventually receive the same packet from the other validators. So each node will create a table like this table, and then it will store the ID and the corresponding public key of each of the nodes. The next step is that each of the nodes, for each of the nodes, it has to calculate a key weight metric, or KWM. But what technically is the KWM? In tree chain, we are allocating a weight to each possible symbol in the output of the hash functions. So as you can see here, for instance, the output of the hash function can be in these ranges. So we are allocating a weight to each of these values. And what we are doing during the KWM calculation is that we add the weight for each of these symbols to calculate the KWM. As an example, to calculate the KWM for this public key, we're following this order, and then the KWM will be 482. The next step is to allocate a consensus code range to these validators. But what is the consensus code range? In tree chain, each of the validators will collect transactions where the most significant bits of the transaction, of the output of the hash of the transaction, starts with a pattern. And that pattern is known as the consensus code range. So in our example, because we had like 5 validators, that consensus code range is just 1 bit. And here we have sort of allocated that the consensus code range. So the way it works is that the nodes will create an ordered list of the KWMs, and then the node with the highest value of the KWM would be allocated to the first consensus code range. And it will continue on allocating the nodes. So the way it works is that whenever this goes back to the transaction level. Whenever a node generates a transaction, so now what we have done is that we have allocated a consensus code range to each of these validators. So whenever a transaction has been generated, assume this transaction has been generated, so the transaction will be stored to the blockchain by only one node, which is responsible for this sort of with this transaction. So in our example, the transaction starts with D. So and then here, if we look at in this table, we'll see that node 13 would be responsible for storing this transaction into the blockchain. So that means other nodes wouldn't attempt to store it in the blockchain, and only node 13 will collect it, verify it, and then append that into the blockchain. So because of this feature, because the validator doesn't need to follow any other algorithm, so then tree chain can achieve a very fast block generation rate, which can lead to forking. And we solve that problem by defining 3 sort of branches of ledgers in tree chain algorithm, which is also as the name suggested. So then we have, so for each of these ledgers, you can consider them as a ledger which is managed by one of those validators, and it's like for the consensus code allocated to one of these validators. So here in conventional blockchains, the consensus is achieved they're saying that the longest ledger would be the ledger which is accepted, but here we don't need that sort of concept, because for each transaction there is only one validator that will store that transaction in the blockchain. Here's a very simple evaluation output. So as I said, there's no processing overhead for storing transactions in the blockchain. So we've measured the processing overhead during the consensus code formation, and we can see that a 50-fold increase in the number of validators increases the processing time by around 20%, which shows the high scalability of tree chain. Thanks, and if you have any question, we'll be happy to answer.